Okay, so for problem number 9, it says suppose the amount of a radioactive substance is given by the function f of t equals 20 times 0.645 to the t, where f of t is the amount in milligrams of a substance at time t years. So part A says to convert that exponential function to the form f of t equals a e to the kt. So something we should notice is that our first f of t follows the form of a b to the t. You should have seen this before. It's just like that ab to the x exponential form. But we want to change it to this. And so first of all, let's look at our initial value. Here for the first one, it's 20. And if we're converting it, you'll notice that here a is in the front and here a is in the front also. So first, our a is still going to be 20. Okay? And so let's look at what this 0.645 represents. This is b equals 1 minus r, right? It's 1 minus r because it's less than 1 and we know it's a decay function. So the main difference between the form we were given f of t in and what we need to change it to is that instead of b to the t, we have e to the kt. So because of this, we need for b to be equal to e to the k. And we know what e is, and we know what b is, so we can use those things to solve for k. So I'm going to go up here, I'm going to say that 0.645 equals e to the k. Okay? So now we need to take the natural log of both sides to get rid of the e. So this becomes natural log of 0.645 equals k. Now it says to round k to 4 decimals. Let me plug this into my calculator real quick. Natural log of 0.645, and I get negative 0.4385. Okay, so we're going to take this and we're going to plug it in here, right? We have 20e to the kt there. So f of t equals 20e to the negative 0.4385t. That's our final answer. Okay, next we're looking at the continuous decay rate and the annual decay rate. So in part A, our answer, we can look at that and we can see, hey, that's a continuous decay function. So when we have that, all we're going to look at is the value of k. So our continuous decay rate is k, which is equal to 0.4385. This is negative. And then for our annual decay rate, we can look at the original function we were given. And here we have that b is equal to 1 minus r, and b is 0.645. So if we say 0.645 is equal to 1 minus r, we'll see that negative 0.355 equals negative r, and so r is equal to 0.355, and that is our annual decay rate.
Hey, surprise, new tutor. So anyway, let's look at number 10 here. Sketch the given function of f of x natural log of x plus 3 and find each of the following. So first let's sketch the graph. I guess the first thing I wonder is, well, what does regular natural log look like? Well, if you recall, there should be an asymptote at 0, and it should pass through this point 1, 0. So, I mean, it should look something like this. Whoops. I mean, it's not that pretty, but should look something along those lines. But we're going to take this graph and we're going to shift it back, right? Shift it back 3 spaces, because that's what's and there. So go here, so back 3, well, that would mean our vertical asymptote's now at -3. And there we go. We just took the graph and shifted it back. So let's think about the vertical asymptote. Well, now we can see, oh, what is this that I've selected? Now we can see that that is a x equals -3. -3, yes, there we go. Domain, okay, well, it starts off at -3, right? And then we just keep going on forever, so -3 infinity. What about the range? Well, range should be all-encompassing here. What this means is that for the function you can only plug in values above -3, but the range can be anything. Okay, is the rate of change between any 2 points in the graph positive or negative? Well, let's just pick 2 points. How about this one and this one? Draw us a little secant line. Is the slope of that line positive or negative? Well, the slope is positive. So really what that means is that this graph is just it's continually increasing. So positive. You can say the graph is always increasing. Okay. Does the rate of change increase or decrease as you move from left to right on the graph? Why? As you move from left to right. Well, think about this. Here's the rate of change here, right? Well, let's move further to the right. Is this slope larger or smaller than the other one? It's smaller. You can imagine that as you keep going, these secant lines are going to get a smaller and smaller slope. So this means that the rate of change is decreasing. Yeah. Rate of change is decreasing. Another word you might have heard from your class is F, concave down. Okay. Is the graph F concave up or concave down? Well, we just said it's concave down. Right, and that's because you can tell based on the shape that it kind of curls over so that there's like a crescent under it. Okay. Limit as x approaches -3 from the right side of f of x. Well, imagine if we follow, I'm going to follow with dots here. Follow this down here. While we keep getting closer and closer to -3 on the x-axis, we go to -infinity. So that would be actually our limit. All right. Okay, so 11 says sketch a graph of logarithmic function f with domain 3 to infinity, range -infinity to infinity that satisfies limit as x approaches 3 from the right side is infinity. Okay, then we got to give a formula. So again, I guess my basic launching point is think, okay, well, graph of regular natural log, just regular good old natural log, looks something like this, if my iPad wouldn't keep slipping on me. Looks something like this, right? We know that the domain of this graph is 0 to infinity, right? The range is -infinity to infinity. So let's try, okay, we want a graph with domain 3 to infinity. So my first thought is let's shift this graph 3 spots to the right. Right? So, okay. There we go. Well, this one has domain 3 to infinity. It has range -infinity to infinity, but x approaches 3 from the right side. We want the limit to be infinity. But here, if you follow, it's -infinity, see? Go down, there we got -infinity. Well, we could fix this by actually inverting this graph. So maybe think about what graph we have right now. Right now we have natural log of x minus 3, because we shifted it to the right 3. If we invert it, we stick a negative sign there, it'll flip over the x-axis. So then that'll work. Yeah. Okay, and this one has domain of 3 to infinity, range negative infinity to infinity, and it satisfies as we approach the limit of 3 from the right side. If we follow this way, we'll get a positive infinity up here as we keep going. So the graph we just came up with was negative natural log x minus 3. Let me get a more clear negative sign there. There we go. Alright, so we are given these functions f and g, and we have to describe the transformation that takes f from g in the correct order. Okay, well, let's think about this. So, first thing we have to worry about is really what's inside of those parentheses, inside of the f function. So, I'd say that the first thing that happens here, because of this 2 right here, is that we horizontally compress by 1/2. Right, and that's because those numbers there that are sort of on the outside of the function, this would be the equivalent of a 2 being like right here in front. So this compresses the graph horizontally. So if you kind of push from it up and down, this is how this will do. Anyway, now this minus 3, well, that shifts it to the right, 3 units. So now let's worry about, what else do we have here? We've got this negative sign here, which should reflect it across the x-axis. Then finally we can shift it up 1 unit because of this +1. So there we go. There's an example. Alright, so now we have to write a formula for the graph that we just transformed in terms of exponential with base e. So we're just looking for an exponential function that you can describe this graph with. So what did we do? Well, remember it should have said we had, should have said that we have, I believe, what, negative f of 2 x minus 3 plus 1, right? Well, since f is e to the x, let's take this negative 2 to the x minus 3, plug it in there for x. So this would be e 2 x minus 3, okay. Well, there's that negative out front, so let's stick that there, and then we add 1. So there we go. That would be our function. So now let's do the same thing for number 13. We have this function h of x, and we want to describe the transformations of f that give us h. Well, again, let's look inside the parentheses first. So first thing that we have is this 5. So let's say horizontal compression by a factor of 1/5. Right. Well, next, let's also look at this +6. Be shift left 6 units. Now there's 3 here. vertical stretch by 3. That's plus 2. B shift up 2 units. And there we go. So now what are the domain and range of H? Well, one thing you can do is you can look at the actual transformations we did, and then look at the domain and range it gives you, and then we can basically find out what the domain and range of our new function should be. So let's do that. Okay, so let's look at the domain. So first, our domain has a compression by 1/5. So this -20 to 15, I'm about to sneeze, hold on, will become, after we apply our compression, 1/5 of 20, negative 20 is -4, and 3, right? Well then we have to shift left 6 units. So this ends up becoming -10, -3. Now let's do the same for the range, but look at the vertical changes. So first let's just write what we got for our domain here. Okay, so range of -1, 12. Well, we said we had a vertical stretch by 3, right? Okay, so that would put our range, we'll do it over here where we did the domain. Vertical stretch by 3, so that gives us -3, 36. Then you shift up 2 units. So, well, from there we get -1, 38. Bingo. So here's the domain and range. Okay, name one point that must lie on the graph of H. Well, we have the point 5, 7 on the regular graph. Or sorry, -5, 7 on the regular graph. So what you can do here is apply the transformations to the point. Well, first let's do the horizontal compression by 1/5, so that would give us now 1/5 times -5, -1, right? Horizontal compression is 1/5, so -5, we get -1. Then we shift to the left by 6, so gives us -7. Okay, that's the x value. Now let's do it to the y values. So we have 7 and a vertical stretch by 3. So 7 times 3 would be 21. And shift up 2 units. So that should be 23. So here's our point, -7, 23. You can double check that also, of course, by using that value for x and this expression right here for h of x. Let's plug in -7. -7 plus 6 is -1. 5 times -1 is -5. F of -5 we know is 7. 7 times 3 is 21 plus 2 is 23. So there we go, it works. All right, now 14. Let's find the formula. The function of g is a transformation of f. So the first thing I notice is it looks like g compared to f, it's kind of squished there, right? It looks like there's definitely some vertical stretch happening, but it looks like it's also compressed horizontally. It's kind of squished in this way, that's horizontal compression, and it's kind of stretched out this way. That's a vertical stretch. So by what factor? Well, it looks like the vertical stretch must be by a factor of 4, because notice we go up to 4 and -4 here, where we used to just go to a -1 and 1. Okay, so I'd say our vertical stretch of 4. Compression, what about that? Well, we used to go out here to 8. Now we're going out here to 4. So it looks like that would be a horizontal compression by a factor of 1/2. Well, we could write that by f of 2x. That's horizontal compression by a factor of 1/2. Now we want a vertical stretch by a factor of 4. So there we go. Be 4 f of 2x. All right, given the graph of g of x, sketch and label a graph for each of the following and state the domain and range. So here we have 2 times g of x minus 4. Well, this 2, this is a vertical stretch, so I'm just going to write some points. Notice that 2, well, this is a vertical stretch of 2, so 2 times 2 is 4, so these get extended. Negative 2, well, times 2 is 4, so that gets extended also. Well, here where we are right now, I gotta take this little graph I have and then shift it down 4 units. So negative 4 goes down to negative 8, 4 goes down to 0, 0, and then, if I can erase properly here, there we go. Here's our graph of h of x. So what's the domain and range here? Well, you can tell it looks like the domain is stayed the same from negative 4 to 4, right? What about the range? Well, here we go from negative 8 to 0, right? Be right here to 0 up here. So, whoops, bracket. Okay. Now this next one. So g of 2 times x minus 4 quantity. So 2 times x minus 4, this 2 on the inside means that you actually have a horizontal compression by a factor of 1/2. So we're going to kind of squish it together this way. Oh, excuse me. And then we're going to shift it over 4 units because of this minus 4 here, right? Okay, well, let's get to work on that. So our compression, we have negative 4, well, this will go into negative 2. This 0 here for x isn't going to change. Wait. So here's the graph we're working with right now. Then we just have to shift it over to the right 4 units. 1, 2, 3, 4. 1, 2, 3, 4. Okay. Well, if I do some erasing now. Oh, hello. Okay. Working an Apple Pencil is not one of my talents. Anyway, here we go. Here's our new graph for j of x. Well, let's look at the domain. Well, we go from negative 2 here to 6. Sorry, positive 2 to 6, my bad. 2, 6. Range, well, we go from negative 2 to 2. So there we go. There's our graphs. All right. 16. So we get the average rate of change over this interval is 4. So we want the average rate of change for each transformation. Well, I'd direct your attention to whatever number is up here in front. So negative 2 times our average rate of change then would be 8. Then 1/3 times our average rate of change, well, that would be 4 over 3. Shifting up or down doesn't actually have any effect on the average rate of change. So we use those numbers on the outside as a guide. Okay. Next, determine algebraically if the function is odd, even, or neither. So let me just write the definition of an even function. I'm just going to pick g as an arbitrary function. If g of negative x equals negative g of x, then I believe this is an odd function. But if g of negative x equals g of x, this is an even function. So these are our definitions. So one way you can check is just plug in negative x for x. So I'm going to do that down here. So square root of negative x squared plus 1. Well, this equals square root of x squared plus 1, because negative x squared is x squared. Well, hey, that's the same. So this function is even.